So this is a part 2 to my first cve-rs video, and I mean the response was mostly great, but there was some confusion. I mean, this is totally fair. Like, the original video was obviously far from perfect.
So, I mean, normally it's totally fine to just respond to questions and comments, but in this case, a lot of the comments were sort of different variations on the same base thing, which came from the fact that there's a little detail in this exploit that I sort of hopped over in the original video. And it wasn't like super important to understand it, but you know, if you want to really understand what's going on, then it is useful. And I just kind of skipped over it because it's a really odd feature of Rust, and it would take time to explain. And at that point, I was sort of getting afraid of making the video just too long. So honestly, sorry about that.
The first thing we need to do is understand a kind of confusing Rust concept, which is called higher rank trait bounds, or HRTBs. And honestly, like, there is a section of the Rust documentation about it, but I found their example kind of confusing, and so I'm gonna give it a shot. And it starts, with this function, which is just an ordinary function that takes a reference and does something with this. In this case, it just prints out the value times 3. Remember, I32 is just an integer if you're not familiar with Rust types. And we can call it, like normally with some reference, and that'll work totally fine. The catch is, what if we want to do something like this? So we'll create a new scope here where we'll define x to be 3 or 2, doesn't really matter. And then we'll say, do something with x. And then maybe we'll go down here and create a different scope where we'll say y equals 3. And we'll do something with y. And we have to borrow it. All right, so this, works totally fine. And we get 6, 9. But what you might, wonder about, given how this exploit eventually is going to go, is what happens if we do this. So we'll say, like, let operation equals do something. We're not going to call it. We're just going to assign the function to a variable. And then we call that here. And this actually works, right? You can run it. It does the same thing. But it's a little confusing if you try to tease out why exactly it works. Because remember that if we just have this here, every borrow has a lifetime. And so this is really just shorthand for a borrow that lasts for some lifetime decay, which is determined when you call the function, right? So the real definition of the function internally is something like this. Now we can imagine writing out here, right? It's easy to say that, okay, this is a function that takes a reference to an I32, and everyone's happy. But what if I have to try and specify the lifetime, right? There has to be a lifetime here. It's just normally the compiler can infer it for us, just like it did down here. But like, what actually is this lifetime? If there's some lifetime, and decay, or some lifetime decay, which says how long the argument lasts. But like, we don't know what that is. In fact, if you look down here, for this call, the lifetime is this scope. For this call, the lifetime is this scope, right? So it's not even necessarily the same every time we call it. This code, should compile. We should be able to do this. So what the heck? How do we get this decay here? And the answer, as Rust's awesome compiler has been yelling at me, is to use a higher ranked trait bound. So what we do is we say, for any lifetime decay that you give me when you call the function, right? So decay is now determined when we call the function. It has type this. So again, this is saying for any type decay that you give me, which is determined when you call the function, it has to have this type. And maybe now you can start to see how this connects to the real exploit, right? But the important part is that if I assign a function to a variable, right, don't just call it like normal, this is what the type actually ends up looking like if it has some lifetime parameter, right? The lifetime parameter is this sort of abstract form. We're saying for any tick A, we don't know what it is yet. We have a function that takes a reference that lasts for decay. So with that, let's switch over to here. And let's try and recreate what we did before. This is just, we have the weird function from before, we have our forever reference, and we're going to try and re-implement it. This time, though, we're going to go through each one step at a time, so you can see exactly what's happening here. And the first thing we're going to do, we'll say step 1 equals weird, is just not even convert it to anything. We'll just look at the original type. So we know how this works, right? T doesn't work like lifetimes. Types don't work like lifetimes. There's no like for T, blah, blah, blah. In Rust, there are in some languages, but not Rust. So T is going to be, inferred normally, but the lifetimes are going to be in their sort of abstract forms. We'll say for any lifetime X and for any lifetime Y, this is going to be a function that takes a reference of length Y to a reference of lifetime X to a unit, and then a reference that lasts X to T, and gives us a reference that lasts Y to T, right? And so, again, I did that in the last video. All right, so this is just like, by following the same rules that we did over here, right? This is just the normal native type of weird. Now, if we want to actually do some sneaky conversions, we can employ contravariance, and we'll do it a little bit differently than we did last time, since I have to type, write out all the types explicitly. So we'll start with just the same thing. Antic y, antic x unit, antic x t, antic y t equals step 1. All right. And then what we're going to do here is, remember, contravariance says we're allowed to make the function arguments more specific. So if I have a function that takes animal, I'm allowed to say, actually, that's a function that takes cats. And in this case, what we're going to do is we're going to go over here and change our x to static. Right? This is totally valid, because anything that lasts for the static lifetime, which is forever, will also have to last for x. So this is a totally valid conversion that we're doing. Then we'll do step 3. Now, only at this point do we substitute in tick A and tick B. Right? Up until this point, all we've been talking just in terms of any lifetime X and any lifetime Y. Now that we have it in this form, we can substitute A for X and B for Y and get fn antic B static unit antic X, antic A T antic B T. All right, that's yep. And so this is the final step, because now we need something that lasts, reference that lasts for tick B to something that lasts forever. Well, something that lasts forever to something that lasts forever, surely satisfies that. And so we can go ahead and pass forever here. Again, this isn't exactly the same as the previous version. If you try to type out the other version, it complains about the well-formedness of these types. But that doesn't mean you can't do it. So yep, and then we need our borrow. And there we go. So now we've re-implemented it, and you can see that, well, first we can see that this works. Yep, so we just get random uninitialized memory garbage. And so, again, this is sort of where the problem is. The problem is in this first line. Right, well, what's wrong here? Remember that this whole thing is only well-formed. This only works if the lifetime tick A outlives the lifetime tick B. Right? In this case, when we have it in our function type, this only works if the lifetime tick X outlives the lifetime tick Y. But there's a problem, which is that we can't put that constraint anywhere, right? All we can have is just this, and nowhere is there any constraint. What we would have to do to fix this is to add constraints to higher ranked trait bounds. So you'd be able to say something like, for any type, or for any lifetime, tick X and any lifetime tick Y, where tick X outlives tick Y, then that would work, because now what would happen is that constraint would be carried along over here. And then when you substitute in, the compiler would check that that tick X outlives tick Y, which in this case is tick A outliving tick B, once we substitute it. And then the compiler would complain and understand what's going wrong. But we can't have that, right? You can see it's all, the syntax is going crazy, because This is not something that actually exists. You can't express this in Rust. So that's why this is so difficult to fix, is because it's a problem in the sense that the actual type of weird isn't something you can express in Rust, right? The type of weird isn't of the form, for any of these lifetimes, I have these arguments and I have this return. It's that, but also you need to make sure that tick X outlives tick Y. So it's an expressiveness problem. And again, like the rest of this is just totally valid, right? We can't, again, at this point, there's no constraints about tick A and tick B because we haven't involved tick A and tick B yet, right? It's all just in terms of this sort of abstract tick X and tick Y. And then, by the time we actually do involve tick A and tick B, it's already too late, right? Our, supposedly illegal reference, right, where it looks like, we have a nested reference, is now gone. All that we have to check here is that tick static outlives tick B, which it does. We're good, right? So that's where the problem is. And to fix it, you would have to somehow be able to encode the constraint into this type. So hopefully that clears it up a little bit. And, seeing it in every step here can help you see where exactly, the problem is. So yeah, that's all. Feel free to leave, more questions in the comment section. I'm very much not opposed to answering questions in the comment section. It's just this was, I felt like a good case of, making an actual follow-up video. So I literally just was about to start editing this when I get pinged, and it turns out the White House put out a press release saying that we should start making memory-safe software. So, good timing, I guess.